Okay, hi everyone, and welcome to this 8 Notes lecture. Hopefully you're all here today for the HSC Maths Advanced lecture. So welcome, my name's Alice and I'll be your lecturer today. I will introduce myself a little bit more in a minute, but yeah, just for now, welcome. So if this is your first time doing anything with 8 Notes, here's just a little bit more about what 8 Notes do. So HO Notes provides a whole bunch of free resources to help HSC students get through their HSC essentially. So there's different things available. There's study notes for your different subjects. There's lectures like these ones given by past students. There's online discussions about your courses, different videos to help you revise, different newsletters that help you stay in the loop about study tips, different subjects, things like that. For when you get to that point during Year 12 when you need to use your ATAR calculator, there's an ATAR calculator in there, some articles with study strategies and tips, and heaps more. So this is just some of the things that we offer. You can find pretty much everything at atarnotes.com. If you want more information on tips or how to use these resources, you can check out the info doc under the resources section of this lecture page. So yeah, essentially we have free notes, free videos, free guides from past students, and if you have questions after the lecture about any of these, the best place to go is in the Q&A section of this lecture if you're watching it live, where current students and past students like me can answer your questions. And if you're looking for even more support, we've got you covered. There's also 8 Notes Plus. This is where you'll find the 8 Notes books that I'm sure a lot of you guys are actually familiar with already. The AI tutors, different flashcards, text guides for all your different English books as well. So this one is a paid service, so if you are looking for a little bit more help, you can Google 8 Notes Plus as well. So that's about it for the intro, I guess. So welcome to the lecture. I'm glad to have you with me today. If you guys are watching it live, the chat function is available, and if you've got any questions about the lecture itself, study tips, things Year 12 related, as you guys are preparing for your last year of school, feel free to pop a question in the chat. I'll be answering them. So yeah, any questions you've got, feel free to pop them in there. So a little bit about me. So I said my name's Alice and I'm your lecturer today. So I am currently studying medicine in Newcastle. If any of you guys are thinking about studying medicine at the end of the year, would definitely recommend Newcastle. Obviously I'm a little bit biased, but I do think it's the best. I graduated in 2022 with 99.3. And in Year 12 I did only 10 units. So I did bio, economics, English advanced, maths advanced, and tuna religion. So yeah, maths was my second best subject. So hopefully I've got some expertise to share with you guys. And I do tutor all these subjects at TuteSmart, and I run the HSC Maths Advanced class. So if any of you guys are looking for a little bit of extra help this year, feel free to join the maths class, or if you want some private tutoring, I'm there. It's heaps of fun, I think, so feel free to join. So this is my third 8 Notes lecture series. So you may have seen me before in some religion lectures or maths lectures. And then with TuteSmart, which is just the 8 Notes tutoring company, like I said before, I do the Advanced Maths HSC class. It's me teaching the course, so I can create specific resources to make sure you achieve your goals. And yeah, if you are looking more for private tutoring rather than the class, I also do some of that, if any of you guys are interested. But anyway, moving on to today's lecture. So today we're going to be thinking broadly about 3 topics and then looking at some study tips. I would say that calculus is the most important part of Year 12 because it makes up like at least half your exam paper at the end. So your calculus includes differential calculus, including everybody's least favorite thing of optimization, and integral calculus. So those are your 2 big topics that you really want to get your head around going into Year 12. depending how your school does it, you may not have looked at integration before. That may be something that they cover in term 1. So if you haven't looked at integration, this will be a good introduction to it. But most of you should have looked at differentiation, or all of you should have looked at differentiation in year 11. You may not have looked at optimization, but we'll take a look at that today, and it's actually not too difficult. You will hear a lot of people complain about optimization, and that being said, I was one of them. I hated it, but I think once you get your head around your optimization, it's not too bad. Then I'm assuming none of you have started doing statistical analysis. Most schools leave this to the very, very end. It's the last thing most schools do. So we'll get you guys a bit of a head start on that because it's an easy thing to get your head around, so you already know what's coming. And then we'll end today's lecture with some study tips for year 12 as well. So the topics we're covering today come from these 2 areas of your syllabus. So your calculus, your differential calculus, applications of differentiation is looking at optimization, and integration as the 3 subtopics of calculus, and then looking at statistical analysis, including bivariate data and your random variables. Now, with maths, I wouldn't say your syllabus is the most important thing. With things like your humanities subjects, you really need to be like head over heels in love with your syllabus. With maths, as long as you sort of know the general topics and the general things included in your syllabus, that's fine. You don't need to know like every single dot point. Like you don't need to know exactly what the dot points are. You need to know the content, but like learning the syllabus itself is not very important. So don't stress about that. Just have a broad understanding of what your syllabus includes. Okay, so we're going to start looking at differentiation. So thinking about differentiation in broad terms, or like the basics of differentiation, we're thinking about the derivative. So your derivative is essentially allowing you to find the rate of change, or like the gradient of a function at a particular point. So yeah, graphically, this is what your gradient is. So the gradient of the tangent at that point. So hopefully you guys remember that the tangent is a line that intersects your function exactly once. So that's what this red line is. And if we're saying that this is our point of interest, the derivative here, we're looking for the gradient of the tangent when it hits that point. Okay, so that's pretty much the big thing you need to know about differentiation, is like, what are you actually trying to find? The reason that that's important is because if you understand what you're actually trying to find and like what the numbers you're doing, I guess like graphically mean, then it becomes a lot easier to do your applications of differentiation, because it's much easier to see how these things translate into like a real life sort of situation. So yeah, big things to remember here is that your derivative is allowing you to find the instantaneous rate of change, okay? Make sure you remember it's instantaneous because it's only at one specific point. Like it's not the rate of change, you know, from point A to point B, it's at like the rate of change at a single point. And that graphically, that means that you're finding the gradient of a tangent. So looking at the basics again with our differentiation, important to remember all of these things are on your formula sheet, so like don't stress about trying to remember them. More important that you just remember how to use them. I think people in maths get a little bit twisted and get a little bit like confused trying to remember all these different rules, but all you have to do is know how to use them. You don't have to remember the rules themselves. They're all on your formula sheet. So we've got the power rule, which is the very, very basic rule of differentiation. So we're looking at the derivative of x to the power of n. What we want to do is bring n down the front, keep our x the same, and we do n minus 1. So quick side note that this will work when your n is a negative number or a fraction as well. Doesn't matter what your n is, you can use this rule. And that's just like your basic rule of differentiation. If you had something like, I don't know, like 4x squared, you'd bring the 4 down the front, so you'd have 4. You'd bring the 2 down the front, so you'd get 4 times 2x, and then 2 minus 1, and you'd end up with 8x as your solution. So it's just like your basic differentiation stuff, really. Then looking at your basic trigonometric differentiations, the derivative of sine x is cos x, derivative of cos x equals negative sine x, and the derivative of tan x equals sec squared x. That's really all there is to that. They do get a little bit more complicated when you start putting fx in there, but we'll have a bit of a look at that later on. Yeah, that's really all there is to it. It's important to remember your differentiation stuff and to be really on top of it because it will help you with your integration. I think one of the big reasons that people struggle with doing integration in Year 12 is because they didn't understand differentiation to begin with. And if you guys know anything about integration, you know it's the reverse of your differentiation. So it's going, from what you've differentiated back to what the original function was. So hopefully you guys get a good understanding through this lecture of your differentiation and what's important about it. And then you'll be set for your integration as well. So some more of the basic rules that are used really commonly is your e to the x. That does come up fairly commonly, something that you do need to know, that the differential of e to the x is just e to the x. And then a little bit of a harder one. For me in Year 12, these were my least favorite differentiations to do. I hated logs and exponentials. I don't really know why, I just did. But these rules are a little bit harder to remember, I think. Or harder to remember that they exist. So we've got the differential of a to the x. So that's where a is any base number. So let's say you might have 3 as your a. And then x is just in your exponential here, you just have to have a pronumeral. So that could be, 3 to the x. That could be 3 to the 2x minus 1. That could be, let's say 6 to the power of 2a. It's just going to be a base number and a pronumeral in your exponential is essentially what this is trying to get at. And so when you've got something like that, what you want to do is you're going to have ln a, so whatever your base number is ln of that number, and then multiplied by whatever your original function was. So let's say we had 3x, or 3 to the x, we'd end up with ln 3 times 3 to the x. And that's all you have to do for the exponentials. So yeah, if you're like me and you don't like your exponentials, just remember that they exist and then you're on your formula sheet, and whenever you see something that has a pronumeral in the power, just know you have to use one of these two rules. So then we've got logs. So log differentiation is something that a lot of people forget that you can do. So it's important to remember that you do know how to differentiate just a base log of whatever, as well as ln. So yeah, a lot of people forget that those exist. So just, I guess, remember that they're there and that you do know how to differentiate your logs. But for ln x, the differential is 1 over x. This does get a little bit more complicated when you've got ln f of x, but for now, we'll just keep it as ln x equals 1 over x, and we'll look at the little bit more complicated version in a minute. And then for differentiating any other log, so anything that's not base e, so log 2x, log 10x, log 27x, whatever, we're going to have log ax equals 1 over ln of your base, or your a, multiplied by x. And those are the very basic differentiation rules that you need to be aware of. The other thing you really need to remember is that these are base forms, but from those base forms, we've got the chain rule. So whenever you have a function that's within a function, you differentiate the same way, but you also have to multiply the result by the derivative of the function inside. So this applies no matter what you're differentiating, whether that's a log, a trig function, just your basic differentiation, an exponential, whatever. If you have a function within your bigger function, so you've got some brackets within your function or something like that, what you need to remember to do is that you differentiate the whole thing first. So you've got gu dash of fx, and you have to remember that you need to multiply the entire derivative of the function by just the derivative of what's inside the function. So you do g dash of fx multiplied by f dash x, and that will give you the correct answer. So this applies every single time, no matter what you're differentiating. You have to remember that if you've got a function within the function, that you then need to do this. We will have a look at some examples later on, so don't get too stressed if that's confusing you. But yeah, the chain rule is super important. No matter what you're differentiating, every time you've got to consider, do I have to use the chain rule here? Okay, so looking at the base forms seems fairly straightforward. And I don't think it actually gets too much more complicated, but you do have to remember, like, what do we do if there's not just x? So for example, what do we do if this is not just x? What if inside the brackets it's like 2x plus 5x squared? What do we do then? Then you get some, I guess, more complex rules to use. So this is the, I guess, more complex rule from your basic differentiation. So what do we do if we have a whole function here and not just an x to the power of n? So then your differential, you bring your n down, multiply it by the derivative of your fx, and then you do your normal fx to the n minus 1. Fairly straightforward, same principles apply. You would have learned this in year 11, so I won't spend too much time on it. Same with these, you should have learnt these in year 11 as well. So we've got y equals sine fx, the derivative of that, you find the differential of just your fx, bring it to the front, and then multiply it by cos fx. Same sort of principle applies with these two. Find your differential of your fx. Just like how you'd have negative sine x, you do negative times your differential times your sine fx. And then again, same principle for tan. Find the differential of your fx here, bring it to the front, multiply it by sec squared of fx. Okay, those ones you should have learnt in year 11 as well, so I won't spend too much more time lingering on those. These ones you may not be so familiar with. I'm pretty sure you do them in year 11. At least your school, I think, should have done them in year 11. But they do tend to confuse people a little bit more, so we'll spend a little bit more time on them. So they are following the same principles as the base forms that we looked at. If we have e to the fx, all we want to do is bring down the differential of our fx, and then we do the exact same e to the fx, because that doesn't change. All we need to do is remember to bring down our differential of whatever is in the power. Okay. Then if we have y equals ln fx, all you need to do for this one, remember that you're not going to have any logs in your final answer. I mean, unless your fx has logs in them, but usually there's no logs in the final answer. All you need to do, differentiate your fx, put it on the top of the fraction, and on the bottom, just put fx again. So you'd end up with f dash x over fx if you're differentiating log e or ln. Now these two, again, my least favorite. I don't know why I didn't like them that much, but I didn't when I was in year 12. But yeah, so if we've got y equals a to the fx, very, very, very similar principle. We have our ln of a, so whatever our base is, ln of that, multiply it by f, the differential of fx, so f dash x, and then multiply it by our same a to the fx. Okay, so really, really similar to the base form. And then finally, we've got, if you're differentiating y equals log a to the fx, you're going to get the differential of fx on top all over ln a times your fx. So with these here, they are all on your formula sheet. So pretty much all you need to know is how do you actually use them. Okay, so don't stress if it all seems a little bit like, oh my gosh, how am I going to remember these things? Because you don't have to. All you have to know is, okay, I need to differentiate a sine equation. Let me look at my formula sheet and see how I do that. Or, I need to differentiate an exponential or a log. Let me look on my formula sheet to see how I do that. As long as you're familiar with where all the different letters go, so you sort of know, like, this A is going to come here, and this is fx, and that's here, and the differential here. As long as you're sort of familiar with all the letters go, practice with them, and you will just get really, really familiar with how to answer the questions. With differentiation, there's not so much that they can ask you, because like your differentiation rules are your differentiation rules. So pretty much how they make these questions more complicated is by, you know, embedding lots of things within one question. So let's say with differentiation, the first thing you have to do is simplify the equation, or you know, with trigonometric expressions, a lot of the time you have to rewrite the expression, and then from there you can then do your differentiation. So yeah, with sort of differentiation questions that you're looking at, you're like, damn, I don't think we actually have a rule to be able to answer this question. First, see if you can simplify it, if you can, I guess, like rewrite it. So let's say they've given you like a reverse trigonometric equation. So let's say like they've given you like sec of 2x squared or something. Firstly, okay, how can I rewrite that into one of the trigonometric equations that I do know how to differentiate? And then you can go from there with your differentiation as well. Okay, so just with these rules, just please remember that they're on your formula sheet. You don't have to remember them. If you're ever uncertain in your exam, when you're doing your homework, whatever, if you're ever uncertain about what the rule is, check it. And the other thing going along with that I can give you as a tip for this is when you're doing your exams, rewrite the formula on your like working out page or like your test page or whatever. Because I found that in my cohort, when we were doing like our HSC, like our exams and things in the lead up to the HSC, a lot of the time people would make mistakes from doing the wrong formula. So, you know, they'd be looking, you know, one line up on their formula sheet or like one line down or something. And because the marker didn't know what they were doing, the answer was just wrong. Okay, so rather, if you write down the equation, number one, you can double check that you've got the right one, because if you're actively trying to write it down, you're going to pick up on the fact that you've got the wrong equation. But two, even if you do have the wrong equation, your marker can at least see what's gone wrong. They can be like, oh, they've done, you know, the wrong trig equation, or they've done the line above where they should have, or something like that. So it'll be easier for the marker to give you marks, so they can sort of see what's gone wrong as well. So yeah, writing the actual equation that you need to, or like the formula that you need to use on your sheet, just helps reduce those like human error mistakes in your exams. So then the other two rules that we want to look at with differentiation, don't you guys worry, I have not forgotten them. What happens to be a lot of people's favorites, or least favorite, the product and the quotient rules. So product rule I find much easier than the quotient rule, because it does not matter which order you do it in. It could be u dash times v plus v dash times u. Or you could do that the other way around, and you could have u times v dash plus v times u dash. Doesn't really matter with the product rule. Doesn't matter which one's u, doesn't matter which one's v. Just have to have one as u, one as v, and put them in there at some point. So yeah, I typically do it alphabetically. So my whatever's first, I do as u, whatever's second, I do as v. And then I start with u dash times v plus u times v dash. So yeah, that's your product rule. Super important to remember whenever you've got two terms that both have a pronumeral in them and they're being multiplied together, you need to use your product rule. I think the product rule usually people find harder to pick up when you need to use it than the quotient rule. I think the quotient rule usually is a little bit more obvious because they've put them in there as fractions. So say with like your quotient rule, you will have like a literal fraction with something on the top, something on the bottom. So it's really easy to pick up that you need to use the quotient rule. Product rule, not as clear cut to like see, I guess like physically see that you need to use it. So you just have to remember anytime you have two pronumerals being multiplied together, you need to use your product rule. So yeah, that's the product rule summed up. There's not a whole lot to it. The hardest part about the product rule is knowing when to use it. So yeah, just remembering that anytime, I cannot stress this enough, anytime you've got two pronumerals being multiplied together, you need to use the product rule. Sometimes they'll make this really obvious for you and you'll have like two sets of brackets being multiplied together. Other times it won't be as obvious. It'll just be things, you know, like say if you had like 2x squared times 3x squared, that would be needing to do, actually with that one, you could probably just multiply them together. But theoretically, you would need to be using the product rule to do that. So yeah, that's the product rule. And then you've got quotient rule. Like I said, it's a lot easier to like physically see and pick up that you need to use the quotient rule in comparison to the product rule. So you'd have something on the top, something on the bottom. Have to remember with this one, super important the order that you do them in, and it's super important what you assign as U and what you assign as V. So whatever is on the top of your fraction is going to be U, and whatever you're dividing by, or whatever's on the bottom of your fraction, is going to be V. Super important that you do allocate those correctly, and important that you write this in the correct order as well. Because when you're doing subtraction, it does actually matter which one is first and which one is second. So we always want to start with U dash times V minus U times V dash all over V squared. Yeah, that's really all that there is to the quotient rule. I can't really explain too much further on that. So yeah, these are also in your formula sheet, so you don't have to remember them. And it is also in your formula sheet the correct order that you need to do your quotient rule in. So if you do ever get confused of, I don't know, to do U dash first or V dash first, check your formula sheet. It's on there. It's worth taking the extra 10 seconds to look on your formula sheet and make sure you've done it correct, than to be second guessing whether you've got it correct. Okay, so yeah, I guess like if another like just little piece of advice, always check your formula sheet. I don't know why some students don't like to check it. They think it's going to waste time. They think they know it, but it is worth the extra 10 seconds it's going to take to look at your formula sheet and find the correct formula. Trust me, it is always going to be worth the 10 seconds. Okay. So then we've got, I guess, like, what does it mean to have the first derivative? So, like we said, the first derivative is about the gradient of the tangent at a particular point. You will see the first derivative written as dy dx, f dash x, y dash. This can really be like any pronumerals technically, although most commonly it is y dash. But essentially, there's actually meaning behind your derivatives, and this is where applications of differentiation become super important, and it's super important that you understand these in order to do your applications of differentiation. So, we're going to say that we're notating our first derivative as f dash a, as sort of whatever we've put into, like the point is x equals a. So if our f dash a is greater than 0, what this means is that the gradient of the tangent is positive, and that means that the graph is increasing at the point x equals a. It's super, super, super important that you remember that when you're doing this stuff, this is looking at just a particular point. So we're just looking at x equals a as one particular point. We're not looking at the function as a whole. So yeah, if your gradient, your first derivative is positive, it means that your gradient is positive and therefore your graph is increasing. Then the converse to that, if your first derivative is negative, so it's less than 0, it means that the gradient of your tangent at the point that you've chosen, so say for this example at x equals a, is going to be negative, and that means that our graph is going to be decreasing at that point. And then the only other possibility is that if the first derivative of your point, so for us of f dash a is equal to 0, that means the gradient of our tangent is exactly equal to 0, and that there is going to be a stationary point at x equals a. So those are the three big things to remember about your first derivative. I think fairly self-explanatory with your first derivative, that if your first derivative is positive, then the tangent, the gradient of the tangent is positive and the graph is going to be increasing. If it's a negative, the gradient of the tangent is going to be negative and your graph will be decreasing. And then if you've got f dash a, or whatever your point is, equal to 0, your gradient of your tangent is equal to 0, and therefore you're going to have a stationary point because it's neither increasing nor decreasing. So yeah, fairly self-explanatory, that one, I think. And so then we've also got to think about the second derivative. So your second derivative is not going to be about the gradient, it's going to be about concavity. So for some of you, this may be the first time you're seeing second derivative. Essentially, you get the second derivative literally by differentiating twice. So, you differentiate whatever expression is first, and then, differentiate it, and then just do another differentiation again. There's no special rules to finding the second derivative. You literally just differentiate twice. And it gets notated as d squared y over dx squared, f double dash x or y double dash. So yeah, whenever you see these two dashes, it usually means that you're looking at the second derivative of something. And so yeah, your second derivative is really important in telling you about concavity. So remembering that concavity is, concave up is our graph looking like this, concave down is our graph looking like that. So if f double dash a, so we're thinking about the point x equals a that we've substituted in, if the second derivative is greater than 0, your graph is going to be concave up at the point that you've substituted in. If your second derivative, so if f double dash a is less than 0, your graph is going to be concave down. And then if f double dash a is exactly equal to 0, there's a possible point of inflection. Now we will in a little bit talk about the use of the word possible. But if f double dash a is equal to 0, there's a possible point of inflection at that point. So we will touch on that possible soon. So don't worry about that just yet. So yeah, again, I would say fairly self-explanatory. If your second derivative is positive, your graph is concave up. In my head, positive and up sort of correlate with one another, which is why I say that's self-explanatory. Maybe you guys don't feel that in your head, but for me, positive and up go together and negative and down go together. So yeah. Now I'm going to show you guys a question, and we'll do a practice question about how you might see this sort of thing come up. This one's actually in a multiple choice question. So at which point on this curve are the first and second derivatives both negative? So what I'm going to do is give you guys maybe like a minute to think about this question, and then we will go through it together. Okay, so hopefully you guys have had a go at this question. If you still need more time, you can pause this video and take as much time as you need. Also, if you guys are watching this and you've done the question and you don't want to sit around and wait, you can also skip the video ahead a little bit as well. So, at which point in the curve are the first and second derivatives both negative? So this is an example of a multiple choice question you might see. So we've got A, B, C, and D. So let's first think about the first derivative, and our first derivative is looking at gradients. So we know if we have a negative gradient, then we're going to have a negative derivative. So the first thing we want to see is which points have a negative gradient. So we know A is going to have a positive gradient, So we can cross that out. It's not going to be answer A. B will have a negative gradient, C will have a negative gradient, and D will have a positive gradient. So we can immediately rule out point A and point D. So then thinking about the second derivative. The second derivative is looking at concavity. So when our graph is going to be concave down, that's when we're going to have a negative second derivative. And so then from there, we can rule that point B is going to have both a negative first derivative because it's going, the gradient of the tangent at that point would be negative. And it is also concave down, as we can see in this point. Whereas point C has become concave up, which means that point C would actually have a positive second derivative. Therefore, B is going to be our answer option. Okay, and this question comes from a NASA sample paper as well. Okay, and so that's how you work out that question. And I guess it's just putting into practice the first and second derivatives and what they graphically represent. So then the other thing to think about with your applications of differentiation is stationary points, which hopefully you guys remember doing in year 11. So stationary points can either be maximums or minimums, or in rare cases neither, which is where the possible point of inflection comes in. So there are two ways that you can determine the nature of a stationary point. So the first is the table of values. So essentially with your table of values, what you're doing is you're going to create a table. You're going to put your stationary point in the table and then do one number on either side of your stationary point also in your table. So let's say the stationary point occurs at x equals 3. You put 3 in the middle of your table and then you do 2 and 4 on either side. Then essentially what you want to do from there is substitute each of those numbers into your derivative equation. So your f dash x, your y dash, your dy dx, whatever you call it. Once you substitute those into that table, you will then see, you'll get given each of the values for your derivative at each of those points. And then from there, you can tell whether something is going to be a maximum or a minimum. So the way that you can determine this is, so your stationary point, when you put that into your derivative, it'll give you 0. So essentially, you're going to have a maximum point if the lower point, so in our example, if we have 3 as our stationary point, your lower point of 2 will have a positive number be spat out, and then your higher number, so let's say 4, will have a negative number spit out, and that's how you can tell that you have a maximum. The reason for that being, at a maximum, your gradient goes positive, then flat, and then it'll go negative on the other side. And then the opposite is true for minimums. You'd have a negative, your 0, and then a positive when you're looking at those 3 numbers. And then you can also determine their nature using the second derivative as well. So in order to do that, you want to find the value of the second derivative at your stationary point. If your second derivative is positive, your stationary point is concave up, and therefore it's a minimum. If it's negative, your point is concave down, and hence it's a maximum. So when finding your stationary points and whether they're a maximum or a minimum, and thinking about which method do I want to choose to be able to, answer this question, I would usually pick the second derivative. I think it's quicker. Unless your second derivative is really hard to find, then I would do the table of values. I just find the second derivative is quicker. It is, I think, a little bit more foolproof, and that there is less room for human error because, you're putting less things in your calculator. You have to do less calculations, things like that. So unless your second derivative is really hard to find, which sometimes it is, it's got to be either really long to find, you don't know how to find it. If you're like me and you just don't want to find the differential of a log, then I would do the table of values. So yeah, table of values is just finding the value of the derivative near the stationary point to the left and to the right. So what I want you guys to have a go at is this question. I always find it really weird doing questions from 2022 because this is the HSC paper that I actually sat. So like it's weird to like look back on it and like be like, oh my gosh, I actually did this. But this is a question from the 2022 HSC. To find the global maximum and minimum values of y equals x cubed minus 6x squared plus 8, where x is between -1 and 7. So it was worth 4 marks. So like these questions do like have a fair few marks attached to them. And like 4 like may not seem like a lot of marks, but like when you think about the fact that you only have like 100 in total, it becomes like a little bit I guess like of a bigger deal, I guess. So like it's 1/25 of your paper right there. So yeah, have a go at this question. Have a go doing it using the table of values if you can. And then yeah, I'll give you guys maybe 2 minutes or so. Feel free to skip ahead or pause the video if you need more or less time. But yeah, I'll give you about 2 minutes. Whoops, that's the answer. Yeah. It'll probably take you longer than 2 minutes, but just for the sake of today's lecture, have a go for a few minutes. Okay, so let's have a look at this question. I'm going to give you a sneak peek to the answer accidentally. But the first step here is to find our first derivative. So if we've got the original equation, y equals x cubed minus 6x squared plus 8, what we want to do, bring that 3 down, x to the power of 3 minus 1 gives you 2, minus the 6 times 2 gives you 12x to the power of 2 minus 1, which is just 1. And then we know that that constant disappears. So we'll end up with y dash equals 3x squared minus 12x. Then, in order to find our stationary points, we're going to make this first derivative equal to 0, and we're going to solve. It's a fairly simple solve, so you get 3x by x minus 4 equals 0. And then your two solutions to that are going to be x equals 0 and 4. From here, we want to pop this into a table of values. So we've got 0 as our first stationary point and 4. And we've picked -1 as the lower limit, the lower number to 0, 1 as the higher number to 0 and the lower number to 4, and then 5 as the upper number to 4. Substituting each of those numbers back into our first derivative equation, we'll get 15, 0, -9, 0, 15. That's quite symmetrical, which is nice. That doesn't always happen, and it doesn't need to happen. Just like so happens to be that way because this is a parabola. So therefore we can say that x equals 0 is going to be a maximum because we've got a positive number, 0, negative number. X equals 4 is going to be a minimum because we've got negative number, 0, positive number. So then in order to find the actual points, we then find at x equals 0, substitute 0 back into your original equation in order to find the y coordinate that matches it. So you've got at x equals 0, y equals 8, at x equals 4, y equals negative 24. However, for 4 marks, you should recognize that that is not all you're going to need to do, okay? With HSC Maths, it's important that you sort of get familiar with how marks are allocated because it'll help you pick up that there is something else that you need to do in this question. First things first, this is question 22. Nothing is going to be that easy in question 22. Second of all, 4 marks is a lot for just finding maximums and minimums. At most, I would probably give that maybe 2 marks, 1 for finding the maximum, 1 for finding the minimum. So recognizing that 4 marks is a lot of marks will help you recognize that this question isn't finished. The other thing that'll help you determine that is that they've given you limits. So the next thing you actually have to do is check what's happening at your limits. So the endpoints, when we're checking them at x equals negative 1, y is equal to 1, and at x equals 7, y is equal to 57. So therefore, our minimum is negative 24, but our maximum is actually 57. Okay, so whilst the question told us that we had to find the global maximum and minimum values here, it wasn't actually through the differentiation that we found out that. It was by using the limits that they had given us to find that the maximum would be 57. The other thing that will help you pick up that your maximum is not going to be 8 is the fact that this is a cubic that's positive. So it's going to keep going up and up and up. So recognizing that if x equals 0, you still have to go up until 7. Okay, so we're not at the highest point just yet. Okay, also recognizing that your minimum and your maximum values are actually y coordinates. Your maximum is not at 0. While x equals 0 is a maximum, the global maximum point is not 0. The global maximum point is, well, in this case, it's actually 57. It's the y coordinate that is associated with the x, okay? Always remember that your global maximum, your global minimum are going to be the y coordinates, not your x coordinates, okay? Also, just remember, in order to find the y coordinates, you do need to sub them into the original equation. It's another mistake a lot of people make, is that they try and find their y coordinates in the first derivative, and your first derivative is spitting out gradients, not y points. Whereas in this, you're finding y equals, okay? Like you're literally finding y. So always remember to do it in your original equation if you're trying to find a value for y. And so yeah, this is just another explanation of using the second derivative to find stationary points. Fairly simple. Find the value of your second derivative at the stationary point. If it's positive, you're going to have a concave up, which means it's a minimum. If it's negative, you're going to be concave down, which is going to be a maximum. So yeah, I think using the second derivative is much easier and much quicker if your second derivative is easy to find, of course. And so the other thing we want to think about is that points of inflection are going to be the points where the concavity of your graph changes. So your points of inflection possibly occur where the second derivative is equal to 0, but this is where the possible comes back. But you also have to check that the concavity changes using a table of values, okay? Because your point of inflection is the point where the concavity of the graph changes. So this might happen when there's a second derivative is equal to 0, but it also might not. So always important to check that your concavity has changed on either side using the similar method to a table of values. So, put your second derivative, whatever's equal to 0, in the middle of your little table, and then, do a number higher, a number lower, and then check your second derivative instead of your first derivative. in the table as well to check that your concavity has changed. So then we've got horizontal points of inflection, which is just like another application of points of inflection. So if a stationary point also happens to be a point of inflection as well, then this is what you call a horizontal point of inflection. So this is when we have a stationary point. This stationary point is also a point of inflection, and therefore you call it a horizontal point of inflection. Same thing, there'll be a point about here as well, where you've got a point of inflection, but at this point it's not stationary, which means it's not going to be horizontal. Okay, that's really all there is to that. And so all of this stuff that we've done so far is all useful for curve sketching with differential calculus. So I guess this is where you the culmination of your differentiation stuff is being able to sketch using differentiation. Now, if any of you guys are like me and you hate sketching, trust me, doing curve sketching with your differentiation is so much easier than just like your regular, like, let's draw a circle. So yeah, all of this is with the aim of helping you to sketch. So that's not the only application of differentiation, but the big application that you're sort of working towards in Year 12 is sketching. So we're going to look at a question. I'll give you guys a few minutes to have a go at this. If you were doing this question properly, it would take you more than a few minutes. So if you do want to have a proper go at answering this question, pause the video. Otherwise, see what you can do in the next 2 or 3 minutes, and then we'll go through it together. Okay, we might go through this question now. If you do need more time, feel free to pause the video. Otherwise, let's get on with it. So looking at part A, so consider fx equals x cubed minus 3x squared plus 3 within the domain of x is between 3 and -1. So for 3 marks, we want to find the stationary points and determine their nature. Fairly straightforward question. So first thing we've got is fx equals x cubed minus 3x squared plus 3. Find your first derivative, so bring that 3 down, do 3x to the 3 minus 1. Then we do 3 times 2, and we bring that 2 down, x to the 2 minus 1, and that constant disappears. So our first derivative is going to be 3x squared minus 6x. Then let's do the same thing for our second derivative. Again, it's literally just doing differentiation on the first derivative. So we bring that 2 down, 3 times 2 is 6x to the 2 minus 1. which just gives us 1 minus 6 as well for the second derivative. So to find our stationary points, we make our first derivative equal 0. So we get 0 equals 3x squared minus 6x. Then we solve that. We'll get your stationary points are x equals 0 and x equals 2. First, when x equals 0, our y point, which we found by putting back into the original, is going to be equal to 3. And at that point, f double dash of 0 is equal to negative 6. Because it's less than 0, this is therefore going to be a maximum stationary point or maximum turning point. Doing the same thing with x equals 2, we pop x equals 2 back into our original equation, you'll get y is equal to negative 1. Substituting 2 into our second derivative here, we're going to get f double dash of 2 is equal to 6. And because that is greater than 0, this is going to be a minimum turning point. Okay, that's all you really need to do there. So for part B, finding the points of inflection, we're looking at our second derivative, which luckily we've already found. So we're going to find our point or points of inflection when second derivative is equal to 0. So therefore, when 6x minus 6 equals 0, and then fairly easy to solve that, x is equal to 1. Then, of course, we're going to check what y coordinate is associated, and we're going to get 1. Then we need to check that our concavity actually changes, because this is not enough to prove that we have a point of inflection. So what we do is, in our table, we have our x values on the top, we have 1, and we've decided to use 0.5 and 1.5 on either side of 1 to check concavity. Then we substitute each of these x points back into the second derivative because we're looking at concavity. We get negative 3, 0, 3. And because the concavity changes on either side of this point, we can therefore say we're going to have a point of inflection. Now for part C, sketch the graph of y equals fx showing all features, don't find the x-intercepts. This is when you can start to plot all your different points that you've learnt about onto your graph. So we found where is our point of inflection, we found our maximums and our minimums. The other thing you want to think about is your y-intercept. Don't have to worry about the x-intercepts, but do worry about your y-intercept, and you should end up with a graph that looks like this. Okay, so the only thing that's not been plotted properly on here is 1, 1 being our point of inflection. I should have plotted that. Whoops, so that's a mark gone. Like if you don't plot like all your features, usually it is a mark gone for each of the features you don't plot. So that'd be 1 gone there. You'd also want to keep that 1, 1 there, but you've learnt about where your maximums and your minimums are. So we've plot each of those in, and then always want to find like where you start, where you end as well. So yeah, then you can use your differentiation to help you solve optimization questions in real world contexts. And these are just when you want to maximize or minimize a particular quantity. It is all just about finding maximums and minimums, doing optimization. So that is differentiation for you. We're about halfway through the lecture, which is good. So hopefully you guys are all doing well. If you guys need a bit of a brain break, pause the video, take a bit of a second to breathe. And then we're going to get straight into integration. So a lot of you, this may be the first time you're looking at integration. Maybe it isn't, maybe your school's already done it. And if it has, then this will be a good refresher, otherwise a good introduction to integration. So integration is the opposite of differentiation because it allows us to find the antiderivative, which is also called the primitive function. And so, for example, the primitive function of little fx is big Fx. And so it's essentially going from, if we found the derivative, how do we get back to what is the original function? And you'll see integration represented by this symbol. So this sort of squiggly S situation, and then you'd put a function in this box here. Okay, so there are two types of integrals. So you've got the indefinite integral, and that gives you the antiderivative and reverses your differentiation process. And then you've got the definite integral. And this will give you, your definite integrals give you area bound by a curve. So we're going to have a bit more of a look at both of these things. So if this is the first time you're thinking about this, don't worry, because we're going to look in much more detail at these. So the first thing we have to remember with differentiation is that when you differentiate, your constants become 0. So for example, if we were differentiating like 3x squared plus 2, we would end up with 6x, and that 2 would essentially just disappear. Okay, so essentially what this means in terms of integration is that there are a whole like family of functions that share the same derivative. Okay, so for example, 2x is the derivative of x squared, but 2x is also the derivative of x squared plus 1, x squared minus 7, x squared plus 2 pi, etc., etc. Okay, so in order to account for that difference, in order to account for the fact that you can't just, magically guess, what the constant is going to be, when we evaluate an indefinite integral, and the indefinite being the fact that we don't know what the constant is, we need to make sure that we account for the constant, the arbitrary constant with a plus c. So essentially, whenever you're doing integration, so let's say we're integrating 2x, okay, which is here, 2x, dx is just what you pop in when you're finding integration. So like we're finding the integral in relation to the x. So the integral of 2x dx is equal to x squared plus c. Okay. Don't worry if you don't know how to do the integration yet. This is just an example that the very first thing I want you guys to know about integration is that if you are doing something indefinitely, you need to make sure you include plus c. Okay, if I can stress anything to you, do not forget the plus c when you're evaluating the indefinite integral, because technically your answer is wrong if you don't include it. And depending how things are being marked in your school, trials, HSC, a lot of markers will actually take the mark off you if you don't include the plus c, because the answer is wrong. So always make sure you add the plus c. So we're going to have a look at the base forms of doing our integration. So similar how we did differentiation before, we looked at the base forms and then the more complicated forms. So what we're looking at here, first of all, is the integration version of the power rule. So essentially, if we are integrating x to the power of n, again, dx is just saying that we're integrating in relation to x. What we want to do is we do x to the n plus 1 on the top of a fraction, and then we do whatever our n plus 1 is on the bottom, and of course, we plus c. Okay, this is where n is not equal to -1. Super important to remember that. But if your n is equal to -1, you end up with 1 over x, integral to relative to x, and then the integral of that, just like always, is going to be ln to the absolute value of x plus c. So fairly straightforward to remember. Again, these are also all in your formula sheet, so you do not have to worry about remembering them. Just know that they're there and that they exist, and how to use them as well. Then some more basics. The integral of cos x is going to be sin x plus c. The integral of sin x is going to be negative cos x plus c. Integral of sec squared x is tan x plus c. Okay, so you will sort of see that this is sort of like your opposites of like your differentiation, because we're going the other way. Okay, and then we've also got integration for exponentials. So here we're looking at the integral of e to the power of x. Again, e to the x doesn't change when we differentiate it, so e to the x will not change when we integrate it. So the integral of e to the x dx is equal to e to the x plus c. Okay, of course we're accounting for the fact that that constant could be whatever. Okay, even though the e to the x doesn't change, that constant can change, so we still have to put in the plus c. And then we've got our second exponential, the integral of a to the x in relation to x is equal to a to the x on top all over ln a plus c. So integration isn't actually too tricky. A lot of people get, I think, I don't know, like intimidated by integration. But it's not too tricky. It's the same as differentiation. You just have to know the rules that are attached to your integration. Okay. So then, just when you thought we were done, there's also the reverse chain rule. So just how we had the chain rule, we also are going to have the reverse chain rule. So essentially we just looked at the base forms, but we do have to remember that when we differentiate, we have to use the chain rule and multiply by the derivative of the function inside. So because we have to do that when we differentiate, that means that there's going to have to be like a matching thing to do when we are integrating. So therefore, to reverse this process when we're integrating, if there's a function inside the function, we need to make sure that the derivative of the function inside is already being multiplied on the outside before we can integrate the whole thing, which is called the reverse chain rule. Now, this sounds really complicated, but I will show you essentially like what this means with a few examples later on. But essentially, we need to make sure that the derivative of the function inside, so whatever the function inside is, we have to make sure that that derivative is already being multiplied on the outside. That sounds super complicated, but we will look at an example, so no stress. So here it is, about looking at the reverse chain rule. Applies no matter what you're integrating. The same way the chain rule applies no matter what you're differentiating, reverse chain rule applies no matter what you're integrating. So essentially what that means here is that if we have f of x n, we have to make sure that we already have f dash x on the outside, and then we can do this integration. Okay, so that's going to be 1 over n plus 1 multiplied by fxn plus 1 plus c. Okay, so in order to be able to do the integration, we have to make sure that this fx, its derivative, is already on the outside. Okay. So same thing goes for all of our trig integration and our exponential integration as well. We have to make sure that this fx, its derivative, is already out here. So we've already got f dash x sine fx before we can integrate it to negative cos fx plus c. Same deal for your other two trig functions. You've got to make sure that your fx has its derivative out here before we can do anything with it. Same thing again with all of these. Okay, hopefully you do recognize this one in the middle as, I guess, the opposite of your log e or your ln. So if you've got the derivative on the top of the function and the fx on the bottom dx, then we're going to have ln fx plus c. Of course, we have to make sure that the top already has the integral, the derivative of the fx. Okay, same thing here. Got to make sure we've got the derivative of our f dash x out the front. Same thing, got to make sure we've got our derivative of our exponential out the front. Okay, now this seems complicated and you might be thinking like, I don't know like how we can do that, how we can just like change things around, but we'll have a look at an example. So I'll give you guys a minute. This is a little bit tricky if you haven't done it already. So I'll give you guys a minute to have a go at this one by yourselves, and then we'll go through it together. Okay, so let's have a look at this one together. So hopefully you recognize that these two are very similar. And hopefully you're recognizing that it's looking like we might have to use this formula here. So the only thing is this numerator is not quite the denominator. Okay, so what we need to do here is not quite the derivative of the denominator, sorry. So what we need to do here is think about what do we need to do to the numerator in order to make it the derivative of the denominator. So first of all, with our denominator, we want to think about the derivative of that is going to be 2x plus 8. Okay, so from there, if we're thinking about the fact that the derivative of this is going to be 2x plus 8, then we need to think about that we need to multiply the numerator by 2 in order to have the derivative on top. Okay, so if we make this on top 2x plus 8, we have just changed this function. Okay, now just like anything, as long as we make things equal, then we can sort of change it how we want. So what we need to do on the outside of our function is then multiply the outside of the function by a half. Okay, the reason that we're multiplying the outside of the function by a half is to account for the fact that we have multiplied the top by 2. Okay, so essentially multiplying a half by what we've already multiplied by 2 on the top essentially cancels that out. Okay, so whenever you're doing integration, if you need to change things around to sort of make them fit so you can do this, all you need to do is on the outside of your integral, account for what you have changed. Okay, so if you've multiplied the numerator by 2, multiply it by a half. Okay, if you have to divide something by 3, then on the outside you're going to be multiplying it, that sort of thing. From here, we then have exactly what we need to make this work. So we're going to end up with a half times ln of our denominator plus c. Okay, and that's all you have to do to use the reverse chain rule. Seems complicated, and then once you see an example, it starts to get a little bit more simple, and the more examples you do, the easier it'll become. Okay, so then if we're thinking about the definite integral, so we've just looked at the indefinite, let's look at the definite integral. So our definite integral allows us to find the signed area bound by a curve between two limits. Okay, so that's what makes it definite, that we're doing it between an exact interval. So say here we're finding the area between 0 and 2 underneath the curve here. Okay, so we're finding the area between the curve and the x-axis. So areas above the x-axis will give you positive numbers, whilst areas below the x-axis will give you negative numbers. Okay, that's because when you integrate them, if they're below the x-axis, you're integrating with negative y values, and above the x-axis, you're going to have positive y values, which is where you get positive area, negative area. Okay, and you can think about that, like say if this was like a square and you had to easily find the area of it, you'd be multiplying like whatever this positive y value is by the x length, which will give you a positive number, but if we were doing this, we'd be multiplying like negative by the positive x length as well. Okay, so to help you sort of understand what this has to do with the definite integral, let's say that we've got this curve and this green area has an area of 4, this yellow one has an area of 3, and this pink one is going to have an area of 2. If you were asked to find the area bound by fx and the x-axis between the points A and D, what you would actually have to do is do 4 plus 3 plus 2. However, if you were actually just doing this using your integral symbol, your calculator would actually consider your your negative 3 as negative. It wouldn't account for the fact that you're actually trying to find area. Okay, so this is why we have to use or evaluate definite integrals using the second fundamental theorem of calculus. Essentially what that means is if we are trying to find the area of something between B and A for fx, if you're trying to find the area between these 2 points, you actually have to find it using big F, so the primitive of B minus the primitive of A. And you actually have to minus the primitive of A to account for the fact that this area is going to be negative. Essentially thinking about like 2 negatives make a positive. So if you do it like this, you will get the proper area and you'll be actually like adding area on rather than taking it away. Okay. Hopefully that makes sense. If it doesn't make sense, ask questions in the chat. Otherwise, we will keep moving on. So the other thing you can do is when you're dealing with definite integrals that have symmetrical limits. So essentially, if your f of x is an even function, then to find the area between a and negative a, if we're using this example per se, all you can do is do 2 times a and 0, okay? Just makes it a little bit easier, less area to find, and you just multiply it by 2, okay? But this is only if they're exactly symmetrical, okay? Then if we've got an odd function and we've got, they're symmetrical with an odd function and we've got a here and a there, if we're not trying to find the area and we are just trying to find the actual value of the integral, then the symmetry on an odd function means that between a and negative a, our function will actually equal 0. Okay, remembering that this is, with the odd functions, the symmetry only works if you're not trying to find the area, just like you're actually just trying to find the value of this integral. All right, so I'll give you guys a minute. We've done sort of a bit of a rapid fire of integrals, so I'll give you a minute, have a go at this, and we'll see how we go from there. Alrighty, so with this question, first thing to consider is the fact that the question is just asking you to find the value of the integral. It's not asking you to find the area. Now, this question stumped a lot of people for that reason, in that they thought that because you were given this, and they were talking about area up here, they thought that the question was asking you to find the area, which it's not. It's just asking you to find the value of the integral between 2 and negative 2. In order to find that integral, we're thinking about each of these areas, you actually want to consider as negative 3 on 2, and then each of your a areas as 1 on 2, okay? This is an even function, which means that we know that this is going to be exactly symmetrical. So in order to find the value from 2 to negative 2 of fx, you do negative 3 on 2 plus a half minus 3 on 2, which will give you negative 2 as your final solution. Okay, so now looking at finding areas bound between two curves. So you can find the area bound between two curves between two values. So b and a can be any two x values. B, just a little side note, always remembering that whatever you put on top is the bigger x number, and then whatever you put on the bottom is the little x number. Again, to me, that sort of makes sense, like the bigger number goes on top, the little number goes on the bottom. But in order to do that, to find the area bound between two curves, all you do is f of x, so the area of the function on top, minus g of x, which is the function on the bottom. Okay, so if we're considering this one here, our f of x is whatever function has the line on top, g of x is the function with the line on the bottom. And then in order to do that, you literally minus f of x, so whatever the actual equation is for f of x minus the actual equation for g of x, you get one final equation that you can then integrate between the limits. Okay, this is best, I think, explained through an example. So I'm actually just go through this example because this is like a new concept and I think it's just easier to explain like this. So this is from the 2022 HSC. So the parabola y equals x squared meets the line y equals 2x plus 3 at the points -1 and 3, 9 as shown in the diagram. Okay, if they don't give you a diagram, always try and draw it if you can. I mean, unless these are really complicated equations. I would always try and draw the diagram, especially when you're trying to find areas between two curves so that you can actually see which one's the top and which one's the bottom. So find the area enclosed by the parabola and the line. Okay, and they've been very nice and they've given you the points as well. Sometimes if this question was, I guess, a bit further on in the paper, they probably wouldn't give you these points and they wouldn't give you the diagram. You'd be expected to draw the diagram, find the points that they intersect at as well. So in order to find this area, we use our x coordinates. So we've got 3 and -1, and we literally minus the two equations from one another. So we've got 2x plus 3 and x squared. Now our 2x plus 3, that straight line is on the top. Like when you're thinking about which function is on the top, you're literally considering which line is above the other one. So we do 2x plus 3 minus x squared because the x squared was on the bottom. Once we've done that, we then integrate it. So we do, 2x squared on 2, which gives us just x squared, plus the 3x on 1, which is just 3x, minus x cubed on 3, which we can't simplify, between 3 and -1. From here, we then substitute 3 into each of these x values, and we'd get 9 plus 9 minus 9. Subtract whenever we find our definite integrals, what we do when we put -1 in. So if we put -1 in, we get 1 minus 3 plus 1 and 3. Pop that in your calculator, and you'll get the area is equal to 10 and 2 and 3 units squared. Remembering, you are finding area, so you do need to have units squared, unless they've given you centimeters, meters, kilometers, whatever. Otherwise, the safest bet is to do units squared. Okay, so there's one more thing we're going to look at with integration. So when we don't know how to integrate a function, we can still sort of approximate the area bound by the curve using a trapezoidal rule. So this is when we've got complicated functions that we don't have a rule to do integration with. So we first want to think about a trapezium, okay? So we're looking at the trapezoidal rule, so of course it's going to have something to do with trapeziums. So if we have a trapezium, maybe it looks like this, the area is equal to a half h times a plus b. Or you may know it as a plus b on 2 times h. Either or, these are the same thing. So the trapezoidal rule involves approximating the area bound by a curve into several trapeziums and then adding their areas up. Now this seems a little bit random, but let's say this pink situation here is the graph of y equals fx. We can divide this into a whole bunch of equidistant trapeziums. So if we've got x1, x2, x3, b just being our final limit, we can divide this into equidistant trapeziums in order to help us approximate the area of our graph. So in proper terms, using the trapezoidal rule to find the area of fx between b and a, all you want to do is b minus a over 2 times n, where n is your number of subintervals or how many trapeziums you've put in. So let's say here we've got 4 trapeziums. And then we do f of a, where f of a is our first number, plus f of b, where f of b is the value of y, and the final number, plus 2 times the values of each of the things in the middle. Okay, this seems a little bit complex. So in a simple form, the trapezoidal rule is h on 2 times the first plus the last, plus 2 times the middles. Okay, where h equals b minus a on n. Okay, this all may seem a little bit complex still, and a lot of people really don't like the trapezoidal rule, but we'll just look at an example so you get a bit of a picture of this. So when we're thinking about this question, it says use 2 applications of the trapezoidal rule to find an approximate value of root 1 plus x squared dx between 2 and 0. Give me your answer to 2 decimal places. First things first, this trips a lot of people up. 2 applications means that you're creating 2 trapezoids. 2 trapezoids means you're going to have 3 x values. And 3 trapezoids means you'll have 4 x values, and so on, so on, so on. So in order to answer this question, if this is what we're trying to find, what we want to do is create 3 x values that are all equidistant from one another. So in this case, pretty easy. We've got 0, 1, and 2. They're all 1 unit apart from each other. Then what we want to do is substitute in each of these values into our fx. So we'd get 1, rounded off 1.414, rounded off 2.236. Then all we need to do here is do a half, okay, which is essentially what you're doing here is b minus a divided by 2. Okay, so this is b, a divided by 2, you're going to get a half of 1 plus 1.41, which is these first 2, and then a half times 1.41 plus 2.236, and that gives you 3.03 to 2 decimal places. Okay, so we've got this, which is our h on 2, so that's half is h on 2, and then we've done only multiplied the 1 once, only multiplied by the 2.236 once, but 2 multiplications of the middle. Okay, so that is integration for you. Not a whole lot to it. It's pretty much just using rules to answer questions. So once you do a lot of practice, you will get your hands around it pretty quickly. So the final sort of, I guess, the content bit before we look at some study tips for today is about statistical analysis. So from year 11, hopefully you guys remember that a random variable is a variable whose possible values are outcomes of a statistical experiment or a random phenomenon. Okay, so essentially random variables allow us to study random processes, essentially by quantifying their outcomes. Okay, so that's a little bit wordy, so we'll have a little bit more of a look at random variables. So random variables are notated using capital letters, and their values are represented by like the corresponding lowercase letter. Okay, so for example, we can define the random variable big X, so capital X, to be the number of heads thrown after tossing a coin 10 times. Okay, so the probability of the random variable X equals little x or lowercase x is the probability of throwing lowercase x number of heads. Okay, so the probability that we throw heads 7 times is the probability of throwing 7 heads. Probability of heads being greater than or equal to 7 is the probability of throwing at least 7 heads. That's really all there is to it. So yeah, like the uppercase is like the actual variable. So let's say uppercase is number of heads equals lowercase, which is like the probability of throwing whatever number of heads. Okay. So your random variables can be discrete or continuous. So this is a fairly simple part of the variables, but a random variable is discrete if its values can be listed or counted. So if you can exactly count every single possible outcome. So for example, the number of heads received after throwing a coin 5 times, you probably wouldn't, but you could like actually count how the values. And then a variable is continuous if its values can take any value along a continuum. So for example, heights of students in a classroom, if you had the equipment to measure it properly, like you could be like measuring down to like tiny little increments. So it can take any value on a continuum. So hopefully in year 11, you learned about discrete probability distributions. Most schools do this at the end of year 11, I think, so hopefully it's fairly familiar to you, or that you haven't probably thought about it in a while. So essentially this is when every single outcome in the sample space can be counted or listed, and you can account for the probability that each outcome will happen. Okay. In year 12, we'll sort of start to think about continuous random variables and how there can be an infinite possible number of outcomes because they lie in a continuum. Okay. So like I said, if we had the proper equipment, heights of students in a classroom could be 1.82 meters, could be 1.64383 meters, could be 1.7930944 meters, etc. Okay, like you could, if you had the equipment, have infinite number of heights. So because there are infinite outcomes, this sort of makes it hard to estimate probability, and so the probability of getting a specific value is going to be 0 because there's an infinite number of values you could pick. So when we're looking at these, it makes more sense to find probability of an outcome lying within a range of values, okay? So rather than trying to find the exact, 1.79234767, it makes more sense to sort of think about what's the probability that a height of a student is between 1.7 and 1.8. So to do this, you will use probability density functions. A lot of people hate these, but once you get your head around them, they're not too tricky. So essentially, a probability density function, or a PDF, is a curve that helps us to see the relative likelihood of an outcome and allows us to find the probability of a continuous random variable falling within a particular range of values, okay? So we could find between 1.7 and 1.8, we could find the probability between 1.7 and 1.72 if you wanted to. So you can sort of find all different types of PDFs. So the famous probability density function, and one that you actually may have seen before, or you may not have known what it was, is the standard normal distribution. Now, you guys can disregard this. You don't actually have to know how to use this formula, although it will come up again in year 12, but you don't actually have to know how to use it, so don't be stressed out by that. But essentially, this is an example of a probability density function that would allow us to find the probability, that someone, this is actually on the bottom are z-scores. Don't worry about z-scores, you do them in year 12, they're fairly straightforward. But the probability that a z-score is between 0 and 1, for example. So with probability density functions, they all have two properties. If your PDF does not have these two properties, then it is not a probability density function, okay? First property is that every single f of x is greater than or equal to 0. Essentially, this is because probabilities will all lie between 0 and 1. You can't have a probability less than impossible, which is 0, and you can't have a probability greater than certain, which is 1. The other thing to consider with probability density functions is that the area under the entire graph is equal to 1. So if we were to find the area between infinity and negative infinity, f of x, the integral of f of x relative to x will equal 1. Now this does make sense because the probability of all outcomes should be 1, okay? If you've got, even though there is infinite number of outcomes, theoretically, if you added all of them up, it's certain that at least one of them would happen, so the area has to equal to 1. Okay, so the area under a probability density function corresponds to the probability of that random variable lying within the interval. Okay, so the probability that x is between k and h is equal to the integral from k to h of f of x relative to x. Okay, so the probability, let's say that x is less than or equal to our little x, is referred to the cumulative distribution function. Okay, a lot of people get super confused between PDFs and CDFs, so CDF being the cumulative distribution function. But essentially, your CDF can be found by doing x, little x, to negative infinity of fx dx. Okay, fairly straightforward. But yeah, I think a lot of people do sort of, the more, this is one of those topics that the more you do it, the more you may become a little bit confused by it. But important just to understand that your CDF is going to give you a equation, your PDF is going to give you a curve. Okay, and your CDF will have an x as one of your limits. Okay, your upper limit will be an x with the CDF, whereas when we're thinking of the PDF, you won't have x in your limits. Okay, so because probability density functions illustrate relative likelihoods, you can use them to find continuous random variables just by looking for the x value, which gives the highest value or the maximum on the curve. So to finish off that speed run through statistical analysis, we'll have a look at this practice question. So I'll give you guys maybe a minute, have a go looking at this. Remembering this is new content, so if you don't know it just yet, that's all good. We'll have time to go through it together in a minute. Okay, so this again from 2022 HSC. Multiple choice question. Consider the following graph of the PDF f of x. What is the value of the mode? First thing to consider with this question, probability density functions means that on here, on our y-axis is probability that something happens, and then this is the outcome on the x-axis. Then we want to think about what is the mode. So if you don't know, like hey diddle diddle, the median's the middle, you add and divide for the mean. The mode is the one that occurs the most, and the range is the difference between. That's something I learned in like year 7, and I don't know why, but it still stuck with me. So mode is going to be the one that occurs the most. So that's going to be which probability is the highest. So therefore, our mode is going to be pi on 4. Okay, so our answer option is going to be C. Important to remember here that your mode, your median, your mean, things like that, they're all going to be the x values, okay? The y value is just the probability it happens, whereas like the mode, the actual outcome that occurs the most will be an x value because the x values are our outcomes. Okay, so that finishes our speed run through the big bits of statistical analysis. So we'll have a quick chat about study tips before we finish up for today. If you guys do have any questions from the lecture, feel free to pop them in the chat. If you have any like questions in general, study tips, year 12, life in general, also feel free to pop them in as well. So some general study tips for maths. First things first, you have to understand that you're going to study for maths really differently to how you study for all your other subjects, okay? Maths is a skills-based subject. It's not like, say, if you're doing, economics, business, legal, those sorts of things where you just, it's a lot of remembering, it's learning how to do short answers, essays, things like that. Maths is a skills-based subject. The only way you're going to effectively study for maths is by practicing, doing textbook questions, past papers, if your teacher's giving you questions, things like that, okay? When doing all those practice questions, I would say super important to keep track of the mistakes that you make. A lot of people shy away from their mistakes. I don't know, they're a little bit embarrassed by it, they don't know why they made those mistakes, but I would say something like the key to me doing well in maths in year 12 was remembering the things that I did wrong. So it was remembering that, let's say like every time I did like a differentiation of a log question, I always messed those up, okay? It's keeping track of those mistakes and recognizing that the areas you're weakest in. So when you do see those questions in your exam, you're prepared for them, okay? You remember the mistake you made last time, and then you can remind yourself not to make that mistake again. And the only way you can sort of do that is to keep track of the mistakes you make. I had a little book that I wrote down all my mistakes in. I'd flick through it before an exam and be like, okay, I've got to remember not to do this, not to do that, that kind of thing. Again, practice makes perfect with maths. It's the only way you're going to be able to effectively study for maths is to practice. And so for that, your past papers are going to be great. They're going to be your best friend when doing revision. And I think it's also important understanding the rationale behind what you're doing. So understanding why you do a certain thing. So, you know, why do all the probabilities in a PDF equal 1? Like that sort of thing helps you understand why you're doing it, so it makes a little bit more sense, the maths behind it. And I think if the maths makes more sense, you're more likely to remember it and to get those questions right. So then just some study tips, I guess, for assessments in general. Start early. There's nothing that I can say more than start early. Just because the more you put it off, the less time you have to perfect it, the less time that you have to work on it, to get those finer details correct. Okay, you want to give yourself the maximum possible time to do a task, because the more time you've got, the more energy you can put into it, the better it'll be. Okay. Second tip, break down what you have to do into specific tasks that you can like action. Assessments, when you get them, especially your 12 assessments, seem big and overwhelming. Particularly things, if you guys are doing a science, doing your depth studies, seem super big, super overwhelming, but break them down into really small actionable bits, and it'll be easier to complete everything in the task. It'll make sure that you're doing everything and you don't miss anything, but it also just means that it's easier to complete and that you can sort of pick like, you know, I only want to do one little thing today, and you don't have to do all this work for your assignment like every single day. You can just do little bits and it becomes super easy to complete the task. And then number 3, kick yourself into gear. do whatever you need to do to, I guess, give yourself some motivation in year 12. There are a lot of things that can distract you, so I guess, eliminate those distractions. Try what works best. If you work best doing like 25 minutes of work and a break, or if you work best by, sitting down, doing an hour of work and then having a half an hour break, that kind of thing. Commit yourself to what you're doing. Give it 100% of your attention so you don't miss any details. And just remind yourself what you want to do. So for me, it was knowing that medicine was the end goal, had to work towards that. And just doing little bits and pieces here and there, I think, as well. The biggest challenge is starting. So just do 5 to 10 minutes if that's all you can do. And yeah. So that's all for today. So thank you guys for coming to today's lecture. If you're watching it live and you've got any questions, feel free to keep tapping in the chat. Otherwise, thanks for coming.